Hi there, it's David Williams again from Okanagan College, and I want to talk a little bit more about Faraday's law and something associated with Faraday's law, and that's Lenz's law. And if you saw the previous video, you would have seen, I would have shown you that Faraday's law is a little bit like this. An induced voltage, there will be an induced voltage anytime that there is a conductor within a changing electric field. And that relationship is the rate of change of the flux with respect to time times the number of loops of this conductor in the field is going to be equal to the voltage that's induced. And we can break that down into looking at whether that's a changing magnetic flux density or whether that's a changing area. Both of those things are going to create a changing flux, which are both going to induce a voltage. Now if we go back to the generator in Faraday's electromagnetic lab, this is from the FET tutorials. So go back to this electromagnetic generator. And instead of having the light bulb like I did before, I've changed it so that it's a voltmeter. And what you'll notice is you can see the voltage is going back and forth between positive and negative as that magnet is being spun by the falling water. And the reason it's going positive and negative is because of the orientation of the magnetic field is changing, or actually the orientation, the direction of the change of the magnetic field is alternating. And so when you have an increasing magnetic field, the voltage will be one way, and when you have a decreasing magnetic field, the voltage will be another way. And in order to figure out what the orientation of that voltage is, we're going to use something called Lenz's law to help us. And Lenz's law states that when a changing magnetic field induces a current, the direction of the current induced is such that the magnetic field created by the induced current will be such that it opposes the changing external field. I put too many such that's in there, didn't I? That's okay. Because the basic idea is that a changing magnetic field is going to induce a current, and that induced current will create a magnetic field, and that magnetic field is going to oppose the changing magnetic field. And there's all sorts of really cool examples of this, and one thing that you should get your instructor to do is to show you the copper pipe experiment. And there's a video of the copper pipe experiment. Actually, it's sort of a stop motion video, and you can find that video here. And the basic idea is that if you have a copper tube and you take a magnet and drop it down the copper tube, and let's say this magnet is small enough so that it fits down the copper tube easily without friction slowing it down. And what you'll find is that you would expect that magnet to fall just due to gravity and a fraction of a second fall at the bottom of the tube. But what actually happens is that the magnet falls very slowly. And that's because of Lenz's law. The magnet, as it falls down the tube, is going to induce a current in the copper tube because the copper tube is going to experience a changing magnetic field. So this changing magnetic field is going to induce a current. And we can see these induced currents. Here are the yellow loops. And they're called eddy currents because they're just sort of spinning in the tube. And now those induced currents themselves are going to create new magnetic fields, and those new magnetic fields, and we would call them the secondary magnetic fields in this diagram, or they call them the secondary magnetic fields, are going to be created by those induced eddy currents. And those secondary magnetic fields are going to be opposite the primary magnetic field here in the red, and so these are actually going to be attractive. And so what's going to happen is the magnet is actually going to be slowed down because of these attractive forces, these attractive magnetic forces created by the eddy currents in the copper tube. And I actually want you guys to see this whole video because it goes into more explanation and sort of shows some stuff that's going on, not just with copper tubes, but also some other examples showing Lenz's law. I'm going to show you a couple of cartoon examples of Lenz's law as well, and how we can use it to relate back to Faraday's law and figure out what the direction of the induced currents are going to be in electrical circuits. So let's go back to Faraday's law here. Actually, I don't need that anymore, so I'm just going to clear it. And then draw a couple of pictures here, a couple of simple examples. So related to the copper tube example, where we're going to have a magnet, and then we have a penny, copper penny. It could be a copper tube or anything like that. And just to think about Lenz's law in general, if we take this copper penny and we move it towards the magnet, we push it towards the magnet, Lenz's law states that there's going to be a magnetic field that's going to oppose that motion. And that reactive force should actually be a little bit less than the force from the motion. So maybe I'll draw a little bit shorter arrow to indicate that. And so Lenz's law is saying that when we have this motion moving towards the magnet, this penny here is going to experience a change in the magnetic field, right? Because the magnetic field at this point is weaker than the magnetic field over at this point. So we're moving the penny towards the magnet, and the magnetic field is getting stronger. So that changing magnetic field is going to induce eddy currents within the penny. And those eddy currents within the penny are going to create currents within the penny. Those eddy currents are going to create magnetic fields, new magnetic fields that are going to oppose this motion. So we're going to have a reactive force going the other way. And so that's really similar to the penny falling in the tube example. But what if we have another example like this? Same sort of setup. We've got a magnet here, but over here, what if we have an electromagnet? So we got some kind of ferromagnetic material wrapped in wire a number of times, connected to a resistor. So we basically have a little electric circuit here. And now we move this electromagnet, this little circuit, towards the permanent magnet. Now when this is not in motion, this is just a circuit sitting there. There's no currents, there's no voltage or anything. But if I move the circuit towards this permanent magnet, this circuit's going to experience a changing magnetic field. That changing magnetic field is going to induce a current, and that current is going to be induced within our circuit here. And then that circuit, that current is going to produce a voltage across here. So we can figure out what the polarity of the voltage is, and we can also figure out what the direction of the current is going to be. And the way that we're going to do that is, first of all, we have motion going from right to left. And so the magnetic field that's going to be induced, well, we're sort of working backwards, right? Because the motion, we're going to create a reactive force that opposes the motion. So that reactive force is going to have to be, just like in the previous one, that reactive force is going to have to be in that direction to oppose the motion. And in order to have a reactive force in that direction, we are going to need to induce a polarity on this magnet with this orientation. So north poles are going to repel each other, so that's how we're going to get the reactive force. Now we can figure out what the direction of the current and the polarity of the voltage drop across this resistor is if we use, going back to the right-hand rule. Now what we're going to do, the right-hand rule where we point our fingers in the direction of the orientation of the magnetic field and our thumb points in the direction of the current. Well, actually, that's what we're going to do now. Previously was we point our thumb in the direction of the current and figure out the orientation of the magnetic field by our fingers. So what we're going to do is put our hands, imagine putting our hand inside those coils there. So we're going to point our fingers then in the direction point our fingers in the direction of the north. There's our thumb. And then we'll imagine wrapping our fingers around this outside loop here. So our fingers are inside the loop, and we're wrapping them around that outside loop, and our thumb is still pointing up. So that's telling us that the current is going in that direction. So the current's going in that direction through this entire wire, back over here. Our induced current is in that direction, and meaning that the voltage drop across this resistor is going to be in that orientation. And so using Lenz's law, we can figure out what direction, what the polarity of the induced EMF, so the induced voltage, EMF, electromotive force, and the direction that the current, the induced current, is going to be in. So if you have any questions, please bring them to your instructor, and hopefully we can figure everything out.